Hello, today I'm going to explain for you the concept of fluidization, which is an important process and relevant in many industrial applications. Basically, whenever you want to promote high levels of contact between fluids and solid, fluidization is a useful process. So it has application in pharmaceutical application, in catalytic reactors, in fluid bed drying system, especially for drying system. For example, when you wanted to dry the solid grains, the fluidization is a common practice. Okay, so here today I'm going to first explain for you the principles of fluidization qualitatively, and then we will look into the mathematics of the fluidization. Okay, so when a fluid passes upward through a packed bed, so here you have this packed bed. When fluid passes upward through this packed bed, the pressure drop across this bed increases when you increase the velocity. Okay, so if you look at the Ergun's equation, you'll see that the pressure drop across the bed is proportional to the velocity, is related to the velocity. So when you increase the velocity, the pressure drop increases. Okay, so but the bed expands when the pressure drop balances the weight of the solid particles. Okay, and that point basically marks the onset of fluidization. Okay, so when the pressure drop because of this flowing fluid balances the weight of the solid particles, that marks the onset of fluidization, and this point is called the point of minimum fluidization. The velocity of the fluid at which the minimum fluidization occurs is called minimum fluidization velocity, and also the porosity of the bed when fluidization occurs is called the minimum porosity for fluidization. Okay, so after the fluidization, after this point, the particle basically, as it is illustrated schematically here, the particle basically start moving independently, and the pressure drop will remain more or less unchanged or constant, even if you increase the velocity. Okay, so this is the description of the fluidization qualitatively, but now we wanted to look into this process mathematically and how to explain, how to describe fluidization mathematically. Okay, first of all, using conservation of mass and assuming the density of the particles are constant, you can conclude that the volume of the solid phase before and after expansion is constant. Okay, so suppose you have this packed bed, cylindrical shaped packed bed, and with the area A, and the length of this packed bed is L1 before the expansion. Okay, so the volume of this solid phase will be equal to L1 times A. But remember, this volume is occupied by both solid and void space. So you need to multiply L1 times A by 1 minus epsilon 1, epsilon 1 being the porosity at the initial condition. So you multiply L1 times A by 1 minus epsilon 1 to just take into account the volume of the solid. So this expression should be equal to the L2 times A, that is the length after the expansion, times area, which remains constant, times 1 minus epsilon 2, which is the second porosity. Okay, so A can be cancelled out from each side of this equation, and then you can write L1 divided by L2 will be equal to 1 minus epsilon 2 divided by 1 minus epsilon 1. Okay, as explained here, L1 and L2 are the heights of the bed that correspond to the porosity epsilon 1 and epsilon 2 respectively. Okay, and this is a useful equation to know. Other equation is that basically you can obtain this equation by writing the force balance at minimum fluidization conditions. Basically, the force associated to the pressure drop, okay, is equivalent to the sum of the weight of the particles and the buoyancy forces. This is a very simple math basically is involved here. You have three forces: buoyancy forces, weight of the particle, as well as the pressure drop because of this flowing gas or flowing fluid. And if you write it down, you will end up with this equation. Here, LMF, basically MF stands for minimum fluidization condition. So LMF is the length of the bed at the minimum fluidization condition, and epsilon MF is the porosity of the packed bed at the minimum fluidization condition, and rho S is the solid phase density of the solid particle, rho F is the density of the fluid, and delta P is the pressure drop, A is the cross section, and G is the acceleration gravity. Okay, so yeah, if you consider this equation, the first equation, which is you can derive it by looking into the force balance, the parameter A, the area, you can cancel it out. Therefore, you can conclude delta P over LMF, that is pressure drop, divided by the length of the packed bed at the minimum fluidization condition, will be equal to 1 minus epsilon MF rho S minus rho F times G. Okay? So now, if you write down the Ergun's equation, okay, we know based on Ergun's equation that the pressure drop can be expressed as using this equation, which is the Ergun's equation. So, so if you substitute the condition, the parameters for the minimum fluidization condition in this equation, you will end up with this equation. So here, basically, all I'm doing here is that instead of delta P over delta L, because at the minimum fluidization condition, delta L is equal to LMF. Okay, so delta P divided by delta L, delta P divided by LMF will be equal to this term. So I just write this term now to the other side of the equation, which is here, 1 minus epsilon MF times rho S minus rho F times G, which is exactly this equation. Okay, equal to the rest is I literally write the same equation down here. Only difference here is wherever we have epsilon, I write epsilon MF, and wherever we have Q, I write QMF. That is the minimum fluidization velocity. Okay, so that is something that you can conclude from the Ergun's equation. So you can rearrange this equation. It's a simple algebra basically is involved here. You can rewrite this equation, rearrange this equation, and if you do so, we'll end up with this equation. Okay, and some people as well prefer to write it in a dimensionless format. So here, note that rho dq divided by mu, rho dq divided by mu, you can write it as the Reynolds number or minimum fluidization Reynolds number. So if you substitute this definition into this equation, you will end up to this equation. So in wherever you see rho dq divided by mu, I write Reynolds number. Here again, rho dq divided by mu, but with the power of 2, that will be Reynolds number with the power of 2, and so on. Okay, so here the first term, the same as what we say for the Ergun's equation. So the first term here stands for the viscous term. The second term stands for the inertia term. And this is the dimensionless version of the Ergun's equation at the minimum fluidization condition for fluidization process. Okay, so so here, for a small particles and when Reynolds number is less than 20, this second term will be less significant compared to the first term. Okay. And when the Reynolds number is very high, that is like more than 1000, and for large particles, the first term will be less significant compared to the second term. So when the Reynolds number is low, or less than 20 to be more accurate, when the Reynolds number is less than 20, this first term is important, and when the Reynolds number is larger than 1000, the second term is important. Okay, so now here I'm going to solve you a simple example just to show you the application of some of these equations we derived today so far. So the example is solid particles having a size of 0.12 millimeter and a density of 1000 kilogram per cubic meter are to be fluidized using air at 2 atmosphere absolute pressure and at 25 degree. Okay, at that temperature, you have the viscosity and you have the density of the fluid. Okay, so if the porosity at minimum fluidization conditions is 42%, fine. The first part of the question is the minimum height of the fluidized bed if cross-sectional area of the empty bed is 0.3 square meter and the bed contains 300 kilogram of solids. That's the first part of the question. The second part is calculate the pressure drop at minimum fluidization conditions, and the third part is calculate the minimum fluidization velocity. Okay, so let's first solve the first part of the question, which is the minimum height of the fluidized bed if you have the cross-sectional area and the mass of the solid. So we know, so let's first solve the the first part. Okay, so we know that the volume of the solid is equal to mass of the solid divided by the density of the solid. Okay, and mass of the solid is already given in the question, that is 300, divided by the density of the solid that is given in the question, which is 1000, that will be 0.3 cubic meter. Okay, and we know the volume of the solid, we already discussed about that in previous slide, but volume of the solid is equal to the length of the packed bed, that is LMF, that the minimum fluidization condition, the length times the area, but you need to multiply that by 1 minus porosity to take into account only the solid phase. Okay, so you multiply it by 1 minus epsilon MF. Okay, so from here you can conclude that LMF, that is the length at the minimum fluidization condition, will be equal to 0.3, that is the volume, divided by A, which is given in the question 0.3, times 1 minus epsilon, and epsilon MF is given in the question 42%, and that will be equal to 1.72 meter. Okay, so that is the length of the packed bed at the minimum fluidization condition. Okay, the second part of the question was about the calculate the pressure at the minimum fluidization condition. So for that we have an equation expressing the delta P divided by LMF. We already discussed about this equation, equal to 1 minus epsilon MF times rho S minus rho F times G. Okay, that was given in the previous slide. So rho S is the density of the solid and rho F is the density of the fluid phase. Okay, so therefore you can write delta P over 1 divided by 7.2, that is LMF, which has been calculated in the section 1, will be equal to 1 minus 0.42, that is 1 minus porosity, times 1000 density of the solid minus 2.374 density of the fluid, which is given in the question, times 9.81, okay, which is the gravity. And here, from here, you can conclude that delta P is equal to 97632 Pascal. Okay, and that's the second part of the question. Okay, and the third part of the question was about to calculate the velocity at the minimum fluidization condition. Okay, so we know that we already derived this equation, that 180 times 1 minus epsilon MF times Reynolds number at the minimum fluidization condition. Okay, that is the dimensionless for a version of the Ergun's equation for fluidization process. We already looked in this equation, divided by epsilon MF with the power of 3 plus 7 divided by 4 times Reynolds number with the power of 2 MF, that is the Reynolds number at the minimum fluidization condition, divided by porosity at the minimum fluidization condition with the power of 2. That is equal to the particle diameter with the power of 3 times density of the fluid times density of the solid minus density of the fluid times gravity divided by viscosity square. Okay, so here basically you have all these parameters that is given in the question. The only unknown is the Reynolds number, because you have the epsilon and you have the D, you have the density, you have the G, and you have the mu. So all you need to do, you need to substitute those values into this equation, which will be basically 180 times 1 minus 42 times Reynolds number MF, which is unknown, divided by 42% with the power of 3 plus 7 divided by 4 Reynolds number at the minimum fluidization condition divided by 42% with the power of 2. That we should be equal to 9.8, that is G, times 1000 given in the question minus 2.374 times 2.374 times 0.12 times 10 to the minus 3 with the power of 3, that is the particle diameter with the power of 3, divided by the viscosity, which is again given in the question 1.845 times 10 to the minus 5 with the power of 2. Okay, and here there's one equation and one unknown, that is Reynolds number, and you can simply solve this equation and you obtain the value of Reynolds number at the minimum fluidization condition equal to 0.083. Okay, and using the Reynolds number, now you can easily calculate the velocity at the minimum fluidization condition, because Reynolds number at the minimum fluidization condition is equal to density of the fluid times the Q, basically velocity at the minimum fluidization condition, times dP divided by mu. So here I can add the index, basically F here standing for density of the fluid, and here from this equation you can write QMF will be equal to Reynolds number, that is 0.083, you just calculated that, times viscosity, which is 1.845 times 10 to the minus 5 divided by rho F, that is the density of the fluid 2.374, that is given in the question, times the particle diameter, which is given in the question, and that will be equal to 5.37 times 10 to the minus 3 meter per second. Okay, and that's the solution to this question. Okay, so let's continue our discussion. So this is basically the Ergun's equation, and the above equation is used to estimate the bed expansion over a wide range of fluid velocities. Okay, so here basically you can apply this equation when velocity is small or large, etc. But for the cases, as I've already explained, that for the cases when the Reynolds number is less than 20, you are not that much wrong if you kind of ignore this term. Okay, you are not that much wrong. Perhaps is not the right expression here. Basically, it is a kind of approximate solution, and it is okay. It's a reasonable approximation to basically ignore the second term and you work with the first term. Okay, so for Reynolds number less than 20 and small particles, the expansion is uniform, and the Ergun equation, which applies to the fixed bed, here this one should be fixed bed, might be expected to hold approximately for the slightly expanded bed. So if you ignore this term, if you neglect this term for the condition where the Reynolds number is less than 20, then you can basically rearrange this equation. That's very simple. You can easily do that. If you rearrange this equation, you will end up with this equation. Okay, so assuming the flow between the particles is laminar, that means you're basically neglecting the second term. If you do that, then the following equation can be used to study the expanded bed. Okay, and here the usefulness of this equation is that here all of this parameter is normally known, because you know the density of solid, density of the fluid, the viscosity, the gravity, and the particle diameter. So all of that could be lumped into one single parameter illustrated by K here. Okay, so for a given system, epsilon or porosity changes with velocity. However, all other terms on the right hand side are constant, so that the velocity could be written as basically Q equal to K capital, that is a constant that incorporate all these properties here, times epsilon with the power of 3 divided by 1 minus epsilon. Okay, so there is one more concept here I wanted to explain, and then we will solve one example, and then we will conclude this video. So that is the terminal velocity of the particle in a bed. Okay, so the expansion of the bed, as we already explained, occurs between the point of minimum fluidization and also the maximum velocity that the particles can reach before conveying occurs. Okay, and that is called the terminal settling velocity and illustrated by QF. So therefore, the operating velocity of the particles are always between QMF, that is the minimum, that is the velocity at the minimum fluidization condition, and this QF, which is the terminal settling velocity. Okay, and there are empirical equations to estimate the QF, that is the terminal settling velocity, on the different conditions. So normally, so these two are the more accepted ones in literature and textbook. When Reynolds number is less than 0.4, there is this empirical relationship between the terminal settling velocity, that is QF, and the minimum fluidization velocity. So in other words, QF divided by QMF will be equal to 90, and when the Reynolds number is more than 1000, this is the empirical equation that relates the terminal settling velocity and the minimum velocity at the minimum fluidization condition, that is QF divided by QMF is equal to 9. Okay? So there is one last example I wanted to solve here, that is a filter of activated carbon is cleaned by passing a hot gas flowing from the bottom to the top, so that the bed is fluidized and the impurities are carried out with the gas stream. Okay, the gas enters the filter at 100 degrees, and the density and viscosity of the gas at those conditions are 1.9 kilogram per cubic meter and 2.27 times 10 to the minus 5 Pascal second respectively. Okay, the particles in the filter are cylindrical pellets with a diameter of 2 times 10 to the minus 3 meter and the length 1.5 times the diameter. Okay, so these are the boundary conditions. The activated carbon pellets have a density of 2550 kilogram per cubic meter. The particles are contained in a cylindrical pipe of 0.3 meter in diameter and 1.5 meter in length, placed vertically, containing 100 kilogram of pellets. Okay, so the first part of the question is experimental measurements show that the length of the bed at the minimum fluidization condition, or LMF, is 0.9 meter. Determine the void fraction at that point. That's the first part of the question. And the second part is determine the pressure drop across the bed at the minimum fluidization conditions. Okay, so this is a relatively simple example, although the question is rather long and may look complicated, but it has a quite simple solution. That is, the first part of the question is to calculate the porosity at the minimum fluidization condition. So we already showed several times today that the volume of the solid is equal to the length. So if this is your packed bed, it's a cylindrical container, so that is the length at the minimum fluidization condition, LMF, and that's the area. So the volume of the solid phase is equal to LMF, that is the length times area, times you need to multiply it by 1 minus porosity to exclude the volume of the void space. Okay, and the porosity at the minimum fluidization condition is represented by epsilon MF. So all of the parameters here in this equation are given in the question except the epsilon MF, which is the question itself. So the volume, that means, will be equal to, so you have the mass, that is 100 kilogram, that is given in the question here, 100 kilogram, and density as well you have. So you have the mass divided by density, that gives you the volume, will be equal to the length at the minimum fluidization condition, which is 0.9, again that is given in the question, 0.9, and times the area, that is pi divided by 4 times the diameter squared. The diameter as well is given in the question, that is 0.3 meter, okay, times 1 minus epsilon f. So you can simply now calculate epsilon f as 0.384. And that's the first part of the question. And the second part of the question was about calculate the pressure drop at the minimum fluidization condition. Again, you have an equation for that. Delta P divided by LMF is equal to 1 minus epsilon MF rho S minus rho F times G. Again, you have all the parameters in this equation except delta P. So delta P will be equal to LMF, that is 0.9, times the rest. And the rest will be 1 minus epsilon. You calculated the epsilon here, okay, times the density of the solid, density of the gas, which is given in the question here, okay, times 9.8. And that will be 13.4 kilo Pascal. Okay, so if I wanted to give a summary here, I would say we have studied the conditions associated with bed fluidization, right? We use the use of the Ergun's equation to describe the fluid condition at the onset of fluidization was discussed. We discussed about the relationship between bed expansion and porosity, and also we talked at the end about the relationships, some relationships, empirical relationships to estimate terminal velocity of particles in a fluidized bed. I hope you found this video helpful. If you are interested, please feel free to subscribe into this channel so that you get updated when I upload new videos. Thank you.